Aloha, we're going to be solving problem 66 in chapter 4. A child slides down a slide with a 34-degree incline, I've drawn here, and at the bottom, her speed is precisely half what it would have been if the slide had been frictionless. Calculate the coefficient of kinetic friction between the slide and the child. So I'll say that if it's frictionless, the final speed will be, I'll define it as capital V. And we know that her, in this case, we're told that the final velocity is half of that. So that's our given information, and we want to find the coefficient of kinetic friction, mu k, between the child and the slide. So you can start by drawing a free body diagram. It's going to be the force of gravity always pointing down straight for the center of the Earth. A normal force coming from the slide, which is perpendicular to the surface, and she's sliding down, so the force of friction will be opposing that motion, going up the slide in that direction. And I think we're just considering when she's sliding down, so not when someone's pushing her down. So those are the only forces acting on her. And we can define a coordinate system so that the x direction is along the plane of the slide. And here is the angle theta. Same with this angle. And this quadrant here sums to 90 degrees, so this is 90 minus theta. But this quadrant here in blue also sums to 90, so that means this angle here is theta. So we can redraw this free body diagram along a coordinate system that just looks a little more intuitive, with y being in the vertical direction. We're free to rotate our vectors around together. And mg is at the angle theta relative to the y direction here. And we know that in the y direction, the forces are going to sum to 0. She's not moving in that direction at all. She's just sliding down. So this is Newton's second law. And we need the component of gravity that's in the y direction, which isn't just mg. It's a component that's in this direction, which is the adjacent side of this triangle I've just drawn here, your right angle in this corner. So mg is the hypotenuse. So this side here will be equal to, the cosine of theta will be this side over this hypotenuse, which is the length, this vector magnitude mg times cosine theta. So Fg in the y direction, that's the mg over g. So that's how we got that. And then from that equation, we can see then that n is equal to mg cosine theta. And in the x direction, whatever her acceleration is, we know that the only force, well, there's two forces. One is going to be the component of gravity, which is pulling her down. And that's going to be mg times the sine of that angle, this component here. And then we're going to subtract, because it's in the opposite direction, the frictional force. So to consider what her final speed is without friction, we would just have only, I'll write this in red, without friction. We would only have the force of gravity. No frictional force, which means that the acceleration would then just be g sine theta in that case. And then we can then use kinematics to figure out what her final speed would be. So we have that equation is g, I'll still write in red actually, just so you know that we're considering the case without friction. This is what we just wrote down, that without friction, sorry, that's hard to read. We have that, so we know the acceleration, and we know that we want to have an equation for the final velocity, vf, which I've defined earlier as v in this case, capital V. So we can use the kinematic equation, and we're going to assume that she starts from rest. She's just sliding down. So I can get rid of that in this equation over 2 delta x, whatever the distance is, she goes down the slide. And to get this velocity in terms of this acceleration, we want to do this because the main difference between the scenario with friction and without friction is just a difference in the acceleration. So that's trying to quantify what the difference between these final speeds, because that's a piece of information that we're given that we're going to need to use. So then VF is going to be just multiplying everything around 2a delta x over, and then we just need to do the square root of that. And this is what called V. And we want to consider now the problem that we're really thinking of is that when there is friction, we're going to have MA be mg sine of theta, again, the component of gravity along the slide, but minus this frictional force. So the acceleration, and we can write the frictional force in terms of the coefficient times n. And we know from considering the y direction, we just did n is mg cosine theta. So we can rewrite this equation. This is the case with friction. So we have this equation for MA. We can just divide out the n's here. So then we have, this is the acceleration we're going to consider, not like in the frictionless case where A is g sine theta, but A will be g times sine theta minus the coefficient of kinetic friction times cosine of theta. And again, we can use this kinematic equation. So even for the frictionless case, we just are going to do the same thing, but we have a different acceleration that we're going to be plugging in. So F is equal to And we also know what they told us is that this is equal to half of this equation over here. And what we're looking for, we're trying to find the coefficient kinetic friction. So I'm just going to rewrite this over here. For the case with friction, A is G times minus whatever distance she goes down the slide. And this is equal to 1/2 of V, where V is really, and this is what we just did, G sine theta times delta X. And we basically just want to use this equation to isolate this coefficient of kinetic friction, and we just want to hope that these delta X's will cancel out, because that's not something we're given. We're only given the angle theta, and we know G. It's just a constant of nature. So we can start just squaring both sides of these equations. So one half squared is 1/4. Just getting rid of the square roots. And then we can just cancel out the delta X's, which is good. We can cancel off the 2, cancel off the G, and then we can just have rewriting this sine theta. So this is good. We just have, we want to find this coefficient, and we know the angle. So then we can just manipulate this equation to isolate UK. So if we imagine adding this term over to the other side and subtracting this term, I'll make this UK cosine theta is equal to, still over on the side, sine of theta, subtracting this minus 1/4 sine of theta. So divide both sides by cosine. You can factor out the sine theta over cosine theta, 1 minus 1/4. And sine over cosine is tangent. And this is really 1 minus 1/4 is 3/4. So 3/4 tangent of the theta, we're told, is 34 degrees. So if you plug this into your calculator, you should get an answer approximately 0.51, and these coefficients are unitless. There's your answer.